All right, guys, we are looking at the first lesson in our probability unit. So first thing we're looking at is what is probability? Probability is the predicted long-run relative frequency. So this isn't something that's always intuitive to people. Probability happens in the long run. So you need many, many trials in order for probability to kind of show itself. The value for probability ranges from 0 to 1. 0 meaning that something has no chance to happen. 1 means that something is certain to happen. So you can really be anywhere in between there, but never less than 0, never bigger than 1. Going along with probability is the law of large numbers. The law of large numbers says if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. So to think about that, think about flipping a coin. This is basically saying if I flip a coin many, many times, the proportion of heads is going to be about 50%. So not necessarily true if I only flip it a few times, but law of large numbers, think about large numbers as doing something many, many times. That's when probability starts to show itself. Okay, so you guys are going to try a short little check here. On page 292, numbers 1 and 2. So go ahead and pause the video. Go ahead and try those, and then come back and see how you did. Okay, so for number 1, so this is talking about what a probability of 0.61 means. So they were talking about U.S. adults and asking them whether or not they ate breakfast. So if we were to ask a large sample, about 61% of them will answer yes. So each sample is not going to be the same, but if it were a large sample, we'd expect it to be right around 61%. Part B then, it's not going to be exactly 61. Like we were saying for Part A, samples are going to vary. And if it is a very big sample, we would expect it to be closer to 61, but it's not always going to be exactly 61. All right, number 2 then was asking us to assign those given probabilities to specific scenarios. So if something is impossible, the probability has to be 0. No chance of it happening. For B, certain, it will occur on every trial. So think about that as like a 100% chance of something happening. So that has to be 1. If something is very unlikely, it will occur once in a while in a long sequence of trials. That's got to be 0.01. Think about that as a 1% chance. Some of you might have selected 0.3 there. Think about 0.3 as a 30% chance. I wouldn't say 30% is very unlikely. So 0.01 is the better answer there. And the last one, it will occur more often than not. So that makes me think more often than not would be over half the time, which goes with 0.6 or like a 60% chance. Okay, so simulation. This is something that we looked at when we did all of our simulation activities with the dice and the calculator random integer generator and flipping the coin. So simulation is just the imitation of chance behavior based on a model. So a model being like when we did the pop bottle experiment, our model was that a 6 was a winner, 1 through 5 was a loser. That's our model. So it's not anything too terribly sophisticated here. So the idea is we repeat many trials before we actually estimate a probability. So based off of our results from the simulation. Some of the basic ways to simulate are tossing a coin, rolling a die, using a calculator for a random number generator, and the random digit table. So a lot of times we'll end up using the random digit table. Now the calculator is actually a little more convenient and streamlined. A random digit table, you have to use the digits 0 through 9 or talk about them all because they're all there. A calculator, you can tell it exactly what to use. The problem with that, though, is on the AP test, there's no way for them to be able to tell if you are actually doing something in your calculator or if you're just making up numbers off the top of your head. So that's why they have to use the random digit table. So that's why we use the random digit table. Okay, so let's look at an example here. So we're on page 301 in your book, and we're looking at number 14. This is where you're all opening your books and checking that out. So we're looking at kind of the model part of simulation here. So 14, on her drive to work one day, Ilana passes through an intersection with a traffic light. The light has probably 1/3 of being green when she gets to the intersection. Explain how it would use each chance device to simulate whether the light is red or green on any given day. So the first thing we're looking at is a 6-sided die. So basically, however or whatever our possible outcomes are for that die, 1/3 of them need to represent green, and then the other 2/3 needs to represent red. So a die is pretty easy. It has 6 sides. So for 1/3, I would just need to pick 2 of those numbers. So let's say I'm going to roll the die once. If I get a 1 or a 2, that represents a green light. A 3 through 6 represents a red light. Now there's more than one option there. You could have picked any 2 numbers to represent green as long as the other 4 represented red. Thinking about table D, so the table of random digits, so that has things 0 through 9, so that's 10 choices. There's not really a way to represent 1/3 with 10 choices, but there is with 9. So what we're going to do is we're going to pick one number off the random digit table. We're going to make 1 through 3 green and 4 through 9 red and ignore 0. So we have to ignore that 0 to get exactly 1/3 here. When we take out the 0, we just have 1 through 9, or 9 choices. So I'm going to make 3 of them green and the other 6 red. C then is looking at a calculator. So a calculator, we can tell it exactly what to do, and I usually pick the least amount of digits, just because it's less to keep track of. So to represent 1/3, I would need 3 numbers. So I'm going to tell the calculator to give me one random number between 1 and 3, and then I'm going to say 1 is green and 2 and 3 are red. So I could have made 2 green or 3 green, as long as the other 2 values represent red. Okay, we're going to look at another example here, and this one's a little bit longer. This one's actually going through and creating a simulation based off of the random digit table. So go ahead and take a look at this one on the next page there. According to the New Jersey Transit, the 8 a.m. weekday train from Princeton to New York has a 90% chance of arriving on time. So that's what you're looking at, a 90% chance. To test this claim, the auditor chooses 6 weekdays at random during the month to ride this train. The train was late 2 of those days. So 2 out of the 6 days the train was late, and it had a 90% chance of arriving on time. Does the auditor have convincing evidence that the company's claim isn't true? So we're going to design and carry out a simulation to estimate the probability that a train with a 90% chance of arriving on time would be late on 2 or more of the 6 days. So here's how we're going to set this up. First thing I need to say is how I'm going to use the numbers on the random digit table. So I know there's a 90% chance of being late, and I know there are 10 numbers on the table, 0 through 9. So if there are 10 numbers on the table, I need one of them to be on time and the rest to be late. So I need to fix this. Okay, so 0 is going to be late and 1 through 9 are on time because 1 through 9 would be 90%, 0 would be 10%. Okay. So if we are looking at 6 weekdays at a time, so out of the 6 days, her train was late too, we want to see what happens in our 6 days. So for our simulation, we're going to look at 6 digits at a time. Okay? And then we're going to record how many zeros are in each chunk of 6. So when I'm looking at the first 6 numbers in the table, each digit represents one of the days. If that digit is a 0, that means the train was late. If it's a 1 through 9, that means the train was on time. So because there were 6 days, we're looking at 6 numbers at a time. If it would have been 5 days, we would have looked at 5 at a time, and so on. Okay, and we're going to do many trials. So here we're going to do 50 and starting at line 101. So this is why I printed off that table for you, because it's a whole lot easier to be able to write on it and kind of group things off. So what you want to do then is you want to set up kind of this chart almost. So really we're recording how many zeros we get because 0 means they were late. So you have a possibility of getting 0 zeros, 1 0, 2 0, and so on, all the way up to 6. So what you want to do then is go through the table. So here's that. Okay, so this is just the same table you guys have. So I just did it on paper and took a picture of mine for you. So what I'm looking at, this is 5 numbers. I need one more to get to 6 here. So these 6 were my first trial. Those represent my first 6 days. And I know 1 through 9 is being on time and 0 is late. So what I'm looking for is, are there any zeros in my first 6 numbers? No, there are not. So that would give me a tally mark at 0. There were 0 days that the train was late. I'm looking at my next chunk of 6 then. So from here to here. So that's kind of what those vertical lines represent. I was just dividing them off into 6s. So in this next one, I'm really looking for how many zeros there are. There are 2 zeros. The train was late 2 out of the 6 days there. So I would put a tally at 2. So what I did is I just went all the way through and did it. 50 is kind of a lot. It took a little while. So then this is what my tally marks totaled out to be. So I ended up with 28 trials where the train was not late at all, 10 trials where the train was late 1 out of the 6 days, 12 trials where the train was late 2 out of the 6 days, and then 3 through 6 there were none. Okay, so what I want to do then, kind of my final conclusion, is to create a probability out of that. So they said to estimate the probability that the train will be late 2 or more of the 6 days. So what I'm interested in is this chunk right here, 2 or more. So total 12 plus 0, 0, 0, and 0 would just be 12 still. And I did this 50 times. So that would mean that my probability of being late 2 or more times is 12 out of 50. So it's going to be how many that I got out, or how many days the train was late 2 or more times. So how many I got out of my 50 trials. If we would have done this 100 times, my denominator would be 100. This numerator would be however many tallies I had in this whole chunk right here. Okay. Now it's important to remember that this is just one spot to start on the line. You could have started anywhere in this whole table, and you're not going to end up with 12 out of 50 every single time. So it's kind of just a luck of the draw, and that's why it's a simulation. So my estimate is 0.24 based off of what I did. So this is the probability that the train will be late 2 or more out of the 6 days. Okay, let's have you guys try a little check here to see how you're doing. So you're not actually carrying out a simulation, but you're just kind of talking about what you would do here. Okay, so try this one on page 299, number 2. Come back and see how you did. All right, so number 2 is talking about breakfast cereal. And each box of cereal has a NASCAR driver's card in it. So they give you the different percentages there. And I need to first decide what random digits I would assign to each person. So the deal is this adds up to be 100%. So for us, it would kind of make sense to go from 1 to 100 for numbers. Now, if I do that, though, I'm going to have to look at 3-digit numbers on the random digit table. And that's going to be highly annoying because the numbers 101 through 999 mean nothing to us. We would have to ignore them, and that's going to make a simulation take a really long time. So something that you can do, kind of a little trick almost, is look at 2-digit numbers, 00 through 99. Okay, so that's actually 100 different 2-digit numbers, which equals out to 100%. So that's kind of a neat trick. So what I did for Jeff Gordon, since Jeff Gordon was 10%, I just started him at 00 and went up to 09. So that represents 10 different values. 00 through 09 is 10 different values. Dale Earnhardt Jr., I just kind of, if I stopped at 9, I picked the next one up at 10 because he was 30%, so that would be 30% total. Okay, and so on with the rest of the drivers. So see how you did, see if yours match mine. If you started this at 1 and ended at 100, just go ahead and shift everything down 1. Okay, so how would I simulate to estimate the chance that a fan would have to buy 23 or more boxes to find the full set? So what I'm going to do is on that random digit table, I'm going to look at 2 digits at a time. That's going to be my number. So look at 2-digit numbers and count how many it takes until I get a number in each category. Okay, so I would want to repeat many trials. So what I'm recording here, this isn't like a tally one like the last one. I would be recording a number. So if I look at that random digit table, so if you look back at yours, the first number is 19. So 19 would represent a Dale Earnhardt Jr. card. The next number is 22. That's another Dale Earnhardt Jr. card. The next one is 39. That's still another Dale Earnhardt Jr. card. The next number is 50. I now have a Tony Stewart card. Next number 34, another Dale Earnhardt Jr. Next number 05, I now have a Jeff Gordon card. So at this point, I've got 3 of the cards. So I would keep doing this until I got one from each of these categories. And the number I want to record is how many 2-digit numbers I had to look at before I got one out of each category here. So that's how that simulation would be done.